Hello. Today I've got nothing to talk about. Although I've got two nothings to talk about, because we use the word zero with two different, the related meanings. We have zero the digit and zero the number. Now let me explain what I mean by that. So zero the digit is how we distinguish these different numbers when we write them. So zero the digit is just about how we write numbers. Zero the number, however, is something rather different. It's the answer to calculations like what's 5 minus 5. It's the solution to equations like x equals 2x. And it's the point in the middle of the number line between the positive numbers and the negative numbers. These are obviously closely related, if only because we use zero the digit to write zero the number, and also because when we say 302, when we interpret that, we mean that's three lots of 100, zero lots of 10, and two lots of 1. So that zero lots of 10 is using zero as a number. So the zero as a digit represents zero as a number. So they're closely related concepts, but it wasn't always like that. In fact, mathematics proceeded for thousands of years without either of these zeros uniformly. So to just illustrate the difference and the similarities between these numbers, let's consider some ancient number systems that had either that had one or the other of these systems, or both, or neither. And we start with the Romans, which is probably the most familiar of the ancient number systems to you. Um, so this is a base 10 system, like ours, but it's non-positional in the sense that the symbol for 1 is different from the symbol for 10 and different from the symbol for 100. Let's not worry too much about the 5 and 50 and 500 business in this for this purpose. So they had no need for a zero digit. So these numbers are already different without needing a digit zero. So here they are, that's 32, that's 302, and that's 320. And there's no need for a zero in the middle of this one to say that there are no tens. There aren't any, you can see that. So the concept of a zero digit was completely unnecessary and would have been completely meaningless and mystified to anybody who used the Roman numerals. And as it happens, I don't think they ever invented the number zero either, though they might have done. But so far as I'm aware, they didn't. But one lot that did were the ancient Egyptians, quite a lot earlier. So the ancient Egyptian number system is rather similar to the Romans. Um, so it's base 10, it's non-positional, and these are the symbols for 1, 10, 100, 1,000, and so on. They didn't have special symbols for 5 and 50 and 500, but that doesn't really make a substantial difference. They wrote their numbers. Well, when you have a non-positional system, you sort of don't need to worry about the order too much in which you write them. But they, as it happens, wrote them mostly top to bottom and right to left. So this is 276, and this is 4,622. Um, so they again had no reason to think about a zero digit, but they did, well, sort of invent a zero number. Here it is. So now these hieroglyphics start life as pictograms, meaning the picture of something, but they acquire meaning that very often has nothing obviously to do um, with the thing it's a picture of. So this, as a pictogram, means the heart and trachea, which is a somewhat gruesome thing for it to mean, but there we are. But it comes to mean beautiful, pleasant, good, and also zero as a number. So let's see how they use that. They used it in two ways that I'm aware of. A set of accounts in 1770 used this symbol to mean that income was exactly equal to expenditure. So you could either have what we would nowadays call a profit of a certain amount or a loss of a certain amount, or it exactly balanced. And they use this symbol to indicate that. And they also use it on architectural drawings as a sort of baseline, and you measure height above it and depth below it. So these are both sorts of zeros. Are they really zero? Well, probably not with the full power of our zero. I don't think this is a convincing zero at all, really, because, and if you stuck a stick in the ground and measured distances from it, you wouldn't say you'd invented zero. Um, and similar, the fact that you measure in two directions from this doesn't really make it a zero, though it's sort of related. And it's clearly using the same symbol as this sort of thing, which is a bit closer to a number zero. Um, it's still not a fully number zero until you've worked out how to do arithmetic and there's no with it, and there's no evidence that they did that. But anyway, they're getting close to a number zero. So, about the same time as this zero appears in Egypt, we have the Babylonian system. Now, that's not base 10, it's base 60. Um, if you want to know more about Babylonian mathematics, you can watch an earlier video of mine about that. That's, I think, rather fun. Anyway, it's a base 60 system. It's positional like ours. The base 60 digits, here there are 59 of them, they didn't have a zero digit, although as a positional system, they were sorely in need of it. And you'll notice they have a sort of intermediate base of 10, just as the Romans have an intermediate base of 5. But anyway, they didn't have a number zero. They didn't have negative numbers. They didn't have a digit zero even, which is really bizarre. So let's see how this works. So it's a positional system. So this is 2 and this is 30. So this, on the face of it, means two lots of 60 plus 30, which is what we call 150. But they didn't have a zero even at the end of numbers. So this could also mean two lots of 60 squared plus 30 lots of 60 and silently no ones. So that's what we'd call 9,000. And they didn't have a zero in the middle of numbers. They just left a gap. So this is two lots of 60 squared and, as it were, silently no lots of 60 and 31s. So that's what we'd call 7,230. So it's a somewhat strange system to our eyes. And the Babylonians themselves never did invent a zero. However, cuneiform numbers weren't just used by Babylonians, they were used across Mesopotamia. And eventually a zero was invented a lot later, around 3,300 BC. This is what it looked like. Oddly, it was only used in the middle of numbers and not at the end. So, but at least some sort of zero digit was present in the writers of cuneiform towards the end of the BC era. Now, the interesting question is whether any spread anywhere. So the sexagesimal system that the Babylonians used was taken over by Greek astronomers. I think it was only used by astronomers, and it was only used for the fractional parts of numbers, and really only of angles. So I think, or maybe others. I think anyway, they only used it for fractions. So a zero also got used by Greek astronomers around the 2nd century BC. Was it, as it were, this zero? So the sexagesimal numbers, apart from zero, arrived much earlier than that. So did this one arrive later and get added on, or did the Greek astronomers invent their own? I don't think we know that. A little bit later, Ptolemy of Alexandria is particularly interesting. He used this symbol as a zero digit for sexagesimal fractions, as in this, so 37 degrees, no 60ths of degree and 23 60th squares. So that's minutes and seconds, as we call them. Now, Ptolemy is interesting because he writes a lot, and in particular, he writes about his mathematics as well as just writing the mathematics. So in some cases, we know how he did his calculations, and we know in this thing, he did not think of this as a number, but rather as a sort of punctuation mark indicating the absence of a number. In other words, this is really just a gap, like the cuneiform gap, but with a thing in the gap to tell you, to reassure you that there really is a gap there. It's not just that I've written it sloppily. So it's really not zero digit as we understand it. It doesn't mean zero lots of 0 minutes, if you like. What it means is I don't have to write anything here, but I'm putting this symbol in here to make sure you know there's a gap between this one and that one. So some people who had a proper zero digit, also very ancient, were the Maya in Central America. They had a base 20 system. Here are their digits. They also had a sort of intermediate unit of 5. So they have a dot for 1 and this line for 5. So it goes up to 19. And they did have a zero digit. And here it is in use. I've rather forgotten this is. It's something to do with phases of the moon or something. But anyway, they were very good astronomers, these Mayan guys. Anyway, so this means this is 8 here, isn't it? So that's 8 lots of 20, which is 160, plus 17, that's 3 15s and 2. So that's 177, that number. And here's a number with a 0 in it. So that's 3 lots of 20 squared, which is 1200 for us. And that's 8 lots of 20, which is another 160, which makes 1360, and nothing else. There we are. So you see they're writing their numbers down top to bottom. So that's a very ancient system. Um, it goes back possibly as long as 1000 BC, so seriously ancient. Um, the zero isn't quite that ancient. I think it sort of appeared sometime around the sort of turn of about 1000 years later, let's say. So that's a proper zero digit. But none of these zeros that we've been looking at have anything much to do with the zero that we use. That all starts much later in India. And here is the guy who did it. So this is much later, right? This is around 600 AD. He lived most of his life in what's now Rajasthan in northwest India, and he composed this thing, which I shan't attempt to pronounce, but it means the correctly established doctrine of Brahma. And you might think that's a religious text, but actually it's a text about astronomy and mathematics, and it's written in verse, which is rather lovely, Sanskrit verse, of course. And here's the first use of decimal numbers as we would recognize them. So base 10 positional system, including a zero digit, which he originally wrote as dot, which again looks rather like a gap, doesn't it? Meaning there's nothing here, but later got zero. It got written that as a zero, as we would. Um, and he was the first to treat unequivocally as a number and negative numbers, and he understood that perfectly. An interesting question is whether this zero in any way relates to Ptolemy's. It's possible. I don't think anybody really knows. There is certainly evidence that Ptolemy's writings reached India, though that would have been a lot earlier than Brahmagupta. Whether the zero, as it were, survived and got adopted by Brahmagupta, I don't think anybody really knows. Of course, that earlier zero was a sexagesimal zero rather than a decimal zero. Anyway, to illustrate that Brahmagupta really knew what was going on here, here is some extracts. He says the sum of two positives is positive, of two negatives negative, of a positive and a negative, the sum is their difference, and if they're equal, it's zero. That's very good, isn't it? The sum of a negative and zero is negative, that of a positive and zero is positive, and that of two zeros is zeros. So he's got addition of all these positive, negative, and zero numbers absolutely right. Um, the product of negative and positive is negative, of two negatives, positive, that's the tricky one, and of positives, positive. The product of zero and a negative, of zero and a positive, or of two zeros is zero. So it's got multiplication completely right as well. There are similar paragraphs about subtraction and division, and they're all completely correct as well. Apart from um, he says zero divided by zero is zero, which is a defensible position, though it's not the one we take nowadays, which is that it's undefined. Um, and he's rather unclear about what he thinks a non-zero number divided by zero is. He certainly didn't get it right, but quite what he meant by what he wrote, I don't think anybody really knows. Anyway, so the basic rules of arithmetic are there. And zero is firmly established as one of the numbers and as a digit. And the relationship between them is clear as well. That his arithmetic had reached, well, Baghdad really, by about 800 AD, and travelled west to Spain, which was then Al-Andalus, a part of the Islamic world. So under the Caliphate, there are a lot of ancient Greek and ancient Indian learning was brought together and translated into Arabic and built upon and it went west to Spain. So what I'm going to focus on now is how we in Europe got our zero as a result of all this. So we have to go back to the medieval European mindset, really. At that point, everybody wrote numbers using Roman numerals, and they calculated using a counting board or abacus. Nobody did calculations in writing at that point. And of course, because their mindset is all about Roman numerals, the concept of a zero digit would have been sort of meaningless to them. The first appearance of Arabic numerals in Europe, apart from in Islamic Spain, so this is in what you might call Christian Spain, in the northwest of Spain, is in this document from a little bit later. And here they're described, but without the zero, which is rather odd because they're not much use without the zero, really, are they? You can't really write numbers if you haven't got the zero digit. So these monks basically were writing this, probably didn't really understand these Arabic numerals. they were thinking these are just sort of like the Roman numerals somehow, and you don't need a zero. They probably looked at the zero and thought, well, I don't understand what that's for, and left it out. I don't know. Um, However, actually, it turns out that Arabic numerals without a zero do have a use. And this is the use for them. So you may know that our current Pope is a mathematician. There was an earlier Pope who was a mathematician. He was Sylvester II. But before he was Sylvester II, he was a French Benedictine monk. And he invented Gerbert's abacus, which is an abacus. So an ordinary, it's really a counting board. So counting boards up to that point had just counters on them, blank counters, stones, pebbles, if you like, which you shuffled around to do your arithmetic. So he invented the idea of writing numerals on the pebbles, so you didn't need to have so many of them. So the pivotal moment is all about Fibonacci, Leonardo Bonacci, um, a merchant, son of a merchant, widely travelled initially with his father when he was still a lad. And he was obviously mathematically gifted, and he learnt about different system of arithmetic and accounting as he travelled around the Mediterranean. And in 1202, he published this book, Liber Abaci. Now, you might think that meant the book of the abacus. Well, it doesn't, because at that point, using an abacus for calculation was so universal that in Italian, the word abaci, if that's how you pronounce it, meant calculation. So this is the book of calculation. And in it, he's the first person to really talk about properly, to talk about in what he calls the 9 Indian figures. And he says, with these 9 figures and with the sign zero, which the Arabs call zephyr, any number whatsoever is written. So that's really interesting, isn't it? Because he's got this sign zero, which isn't one of the figures. It's not a digit. So he's thinking of zero as just a sign indicating the absence of a digit. Remember his mindset about and his audience's mindset about Roman numerals. So in Roman numerals, you don't need a sign to indicate there are no 10 digits. With these ones, you do. And by the way, we'll come back to this point. He didn't use decimal fractions. He's only talking about decimal whole numbers. Ironically, given the title, he's the first person to start trying to persuade people to do arithmetic in writing rather than with a counting board or an abacus. And as you shall see, this whole business of using Indian numerals and doing calculation in writing took hundreds of years to settle in Europe. So I said there were two meanings for zero, one of which is the digit. Actually, there are two meanings for the digit zero. So for us, as I mentioned earlier, 302 means 3 lots of 100, 0 lots of 10, and 2 lots of 1. So we're appealing to zero, the number here, and multiplying it by 10. That is not what Fibonacci meant. He thought 302 meant 3 lots of 100 and 2 lots of 1. Obviously, you get the same answer from that sum as that one, but there's a subtle difference here. You don't need to understand the concept of zero in a number and know how to multiply it by 10. You just know that there aren't any tens here. So it is different, and it's more like Roman numerals, which is the system that everybody was used to. In other words, his interpretation of 302 is very much like the way people would interpret CCCII as meaning 3 lots of 100 and 2 lots of 1. And silent on the fact that there are no tens there. So the history of Arabic numerals in Europe after that is a bit it's long and complicated and includes the famous bit that 100 years later, pretty much, in Florence, Arabic numerals were banned because it was thought the zero facilitated fraud, which in a sense it does. You can easily change 37 into 370 without you don't have to use a zero for that. You could easily change it to 371 for that matter. Anyway, it was banned. They were banned, but it didn't last for long. But now look at this. So this is getting on for 300 years later. This French guy, Nicolas Chouquet, was still having to explain decimal numbers to his audience. And he said the 10th figure does not have or signify a value, and hence is called cipher or nothing or figure of no value. So zero still hasn't really got a number. He's still thinking of zero as just a zero digit as just a sort of gap in the number, like the Babylonians had. He also rejected the idea of zero as a solution to the equation, although By this point, algebra was beginning to get going. Again, it became another Arabic import to Europe. And so you can easily write down equations to which we would say zero is the answer. And at that point, people were saying it doesn't have an answer. Another 100 years or so, the decimal fractions got to Europe. So, although they first appeared in the Islamic Golden Age again, written by this guy, it was the Flemish, actually, he's really an engineer rather than a mathematician, Simon Stevin, who wrote this book, which is about tenths, it's called. And he introduced decimal fractions, or at least I don't know whether he was the first person to use them, but he certainly advocated them, and people took notice and they sort of started using them after him. But his notation is horrendous. Look at this. This is the way we'd write a particular number. This is the way he wrote it. These are tenths. These are hundredths. So this is as it were 184 times 10 to the 0 plus 5 times 10 to the minus 1 plus 4 times 10 to the minus 2, if you like to think of it that way. It's a pretty complicated business, but he is using zero as a digit by now. So another 100 years on, or thereabouts, René Descartes, who developed a lot of modern mathematical ideas and notation, and it's about this time, it might not be him, who first wrote something like this, which says unambiguously that what we're doing here is that this middle digit here means b times 10, even when b is 0. So that really does mean that we're thinking of 0 as a proper number and putting 0 on the same footing as the other digits. But notice what time this is. It's the 17th century, dawn of the age of enlightenment, and we're still only just getting to the point where 0 is another number and 0 and another digit along with the others. And another step was taken, well, not another 100 years later, but quite a bit later. So John Wallis, professor of geometry at Oxford. So he it is who invented the number line that we all use at school nowadays. Um, and he's still trying to persuade people to accept negative numbers and zero, because they're still not really accepted, and even now in the middle of the 17th century. Um, and so he writes here that -3 doth as truly design points D. I think he means what we'd say designate. So -3 doth as truly designate point D as +3 designated point C. So, but he's having to labour the point, right? Even in the middle of the 17th century, get people to accept negative numbers and zero. And negative numbers are still being called imaginary numbers at this point because people didn't really hold with them. And even he hadn't really got this right yet. He still thought that if you took a positive number and divided by a negative number, the answer was greater than infinity, whatever that's supposed to mean. So he still hadn't really got that right. So let's look at this. So in Oxford, the 1680s, John Wallis has invented the number line. Isn't that wonderful? Actually, it's probably more wonderful than we think. We think of it as pretty trivial nowadays, but it's probably really quite an important thing that to get people to understand negative numbers. Anyway, he still hadn't got the rules of arithmetic right that Brahmagupta had laid out 1,000 years earlier. Meanwhile, over in Cambridge, Isaac Newton invented calculus, discovered the rules of gravity, and made all sorts of other wonderful discoveries. So I don't wish to make any remarks about the superiority of one or other of the ancient universities, but there we are. So that's the story of zero. I hope you enjoyed it.